We're going to do kind of a simple example of linear independence so you can get your head around the definition. All right, so the idea is, I'm going to rewrite the definition in terms of this problem, that I've got these two vectors in R3. I would like to determine whether or not this set of vectors, these two vectors, are linearly independent. And so in terms of the definition of linear independence, if we find out that C1v1 plus C2v2 is equal to the zero vector, if that means automatically that C1 the constant and C2 the constant are both equal to 0, then S is going to be linearly independent. Otherwise, it's linearly dependent. Okay, so again, we're going to use that definition in terms of these particular vectors. I'm going to write them as column vectors when I go ahead and write out the equation here. So we want to let C1 and C2 be arbitrary. I have these two column vectors. And you can go directly to a matrix if you want, but I want to show you where these equations come from, because that's really what I want to work with, the definition here. Okay, so that's what the definition tells me to work on. And if you take that one step further, you're going to get C1 plus 6C2, that has to equal 0. A negative 4C1 plus 3C2 has to equal 0. C1 plus 2C2 has to equal 0. All right, so you can either solve this system as it is, or you can go ahead and turn it into a matrix, which is what I want to do. Okay, and again, you could have gone directly from this step up here, right, to a matrix, but I want to show you really what we're doing is we're using the matrix to solve this system according to the definition of linear independence. Okay, so here's my new matrix, and it's going to be augmented, so it turns into a 3 by 3. So the coefficients are 1 and 6, right? And then, of course, I've got my solutions. It's a homogeneous system. Negative 4 and 3 for coefficients in the second row, and 1 and 2 for coefficients in the final row. All right, now, since we're allowed to use the calculator now because we proved in the first test that we're really good with row reduction by hand, I've already programmed this in. So watch, I'll prove it. I already programmed in A to the calculator. There's A. And all I have to do is go to row reduced echelon form, and then go ahead and put A in there. And sure enough, it gives me back this matrix row reduced. So I always put a little squiggly line to show that I've used the calculator. You can do whatever you want. Here we'll make it clear I've used row reduced echelon form. So we get as our answer, here I'll prove it. Whoops. 1 0 0 0 1 0, and then all zeros in the bottom. All right, so that means that 1 times C1 has to equal 0, because here's my C1 column, here's my C2 column. That also means that 1 times C2 has to equal 0, and that means, of course, that C1 and C2 are both equal to 0. What does that mean? That means that S is linearly independent. And we're done.